All right, today we're diving into a new framework that could honestly be a game changer for AI safety. It's a set of mathematical guardrails called Certifiable AI Safety Theory, or CAST for short, and it's designed to keep a leash on even the most powerful AI systems out there. So what's the big problem it's trying to solve?
Well, it really gets to the heart of the matter, doesn't it? How in the world do you build a safety valve for an AI that can literally write and execute its own code? These tool-using AIs are unbelievably powerful, but that power brings with it some pretty unpredictable risks. How can we possibly guarantee they'll stay within the lines we draw for them?
Well, the folks behind this new theory believe they have a rigorous mathematical answer. This isn't just a list of best practices or friendly suggestions, it's a complete theory for building systems that are provably safe. So let's break down the really cool ideas that make this whole thing tick.
Okay, so the first big idea is that CAST isn't some kind of occasional spot check. It's a permanent deployment gate that's baked right into the AI's architecture. I mean, every single action the AI even thinks about taking has to pass through this gate in real time, no exceptions.
The best way to picture it is like a bouncer at a club, a really, really smart and fast one. Before the AI can do anything, call a tool, write a line of code, whatever, it has to get checked at the door. The gate's one and only job is to figure out, is this action certifiably safe? If the answer is yes, it gets in. If not, it's stopped cold.
So you've got this super smart bouncer, right? But how does it actually know what's safe and what isn't? Well, that brings us to the second key idea. This gate isn't just guessing. It has a mathematically precise rulebook that it has to follow.
And that rulebook is called a Convex Safe Set. Now, instead of fuzzy rules like don't be harmful, this creates a precise mathematical map. You can literally picture it as a space. Every possible safe action exists inside a defined boundary on this map. So if the AI proposes something that falls outside that space, the system knows instantly that it's unsafe. Safety is no longer just a vague concept, it's a verifiable location.
And this visual right here, it makes that whole concept just click. That green area is our safe set. That's the rulebook. Any action that lands inside it, like that little green dot, gets the green light. But that action represented by the red cross, it's clearly outside the boundary. The system sees this in a flash and flags it as unsafe. Simple as that.
All right, so we've got our gate and we've got our rulebook. Now let's look at how this all works in practice. What's the step-by-step process this gatekeeper uses to make its decisions?
This is the heartbeat of the system, what the paper calls the master equation. It's a constant loop. First, the AI proposes an action. Second, the gatekeeper immediately starts monitoring it, running super fast statistical tests to see where it lands on that safety map. And third, it either certifies the action and lets it through, or it hits the brakes and triggers a safe fallback. It's this vigilant, constant monitoring that makes the whole system so strong. And check out this graph. It shows that monitoring process in action perfectly. The system is constantly gathering evidence. For any unsafe actions, those are the red and orange lines, you can see the evidence of risk just piles up exponentially, which triggers a super fast rejection. But safe actions, like that green line, always stay well below the alarm threshold. It's a system that's built to fail fast and, most importantly, to fail safely.
Okay, but what happens when the bouncer says no? When an action gets rejected? This is where CAST gets really, really clever. Instead of just stopping the AI in its tracks, the goal is to actually guide it toward a better choice.
You know, most safety systems are just blockers. They're like a brick wall. The AI runs into it, stops, and that's the end of it, which obviously hurts performance. CAST, on the other hand, acts more like a helpful GPS. Instead of just shouting, "wrong turn," it finds the closest safe alternative and reroutes the AI. It basically projects the unsafe action to the nearest point that's inside the safe set, allowing the AI to still get its job done, but in a way that is verifiably safe.
Okay, so checking a single action is one thing, but what about maintaining safety over thousands or even millions of actions? A tiny, tiny error, if you repeat it over and over again, can eventually add up to a catastrophe.
And this is another one of CAST's big innovations, managing long-term safety with what it calls a global risk budget. The best way to think about it is like a financial budget, but for uncertainty. At the start of a mission, the system gets a total allowance for risk. With every single action it takes, it spends a tiny little fraction of that budget. This mathematically guarantees that the total accumulated risk can never ever go over a predefined limit, even if it runs for 1,000,000 steps. And tied right into that, CAST also guards against something called safety drift. As you can see here, an AI could start off in a clearly safe state, that green zone, but over time, with each little step, it might creep closer and closer to the unsafe red zone. CAST actually monitors this trend, this drift, and it can step in before the boundary is ever crossed, making sure the system stays firmly and securely in the green for its entire run.
So when you bring all these ideas together, the gate, the rulebook, the guidance, the budget, you end up with a theory that is surprisingly practical and, well, realistic.
And that's maybe the most important takeaway here. This whole framework is built for the real world. It doesn't assume all the data is going to be perfect and clean. It's specifically designed for the messy, complicated reality of tool-using AIs, where the output of one action immediately becomes the input for the next. It's built for that kind of complexity.
Now, it's really important to be clear about what CAST is and what it isn't. This is not a magic bullet for morality. It doesn't teach an AI how to be good. It is a powerful enforcement mechanism. We, the humans, have to define the rules. CAST is the engine that enforces them. So if you can write down a safety rule in mathematical terms, CAST gives you the blueprint to enforce it with mathematical certainty. But the responsibility for defining the right rules, that still falls squarely on us.
And that leads to the ultimate promise of this whole theory. The paper sums it up with this powerful idea. Unbounded tail risk, that's the nightmare scenario in AI, right? The unpredictable, catastrophic failure that we can't foresee. CAST's goal is to turn that into quantified, auditable residual risk. In other words, it aims to take a terrifying unknown and turn it into a known, measured, and manageable variable. It gives us the tools to decide exactly how much risk we're willing to accept and then to prove mathematically that our systems will honor that limit. And that leaves us with the ultimate question: what rules will we choose to write?